Ionic bonding, it's one of those topics that pops up on pretty much every single chemistry exam. And honestly, it trips a lot of people up. But what if I told you that you could completely master it in just the next few minutes? What if you knew exactly what the examiners are looking for? Well, stick around, because today we are cracking the code. So here's our game plan. First, we're going to get inside the examiner's head. Then we'll figure out what actually motivates atoms to bond in the first place. We'll watch the main event, the great electron transfer, and then feel the powerful attraction that follows. After that, we'll see how all this tiny, microscopic stuff explains a very real-world mystery. And finally, I'm going to give you a super simple checklist to make sure you nail your exam answer. You ready? Let's do this.
Okay, first things first. To win the game, you gotta know the rules, right? So let's figure out what the examiners are really looking for when they ask you about ionic bonding.
Look, it all boils down to this. When that examiner is looking at your answer, they have a mental checklist. They are hunting for 3 specific ideas. If you hit them, you get the marks. If you miss them, well, you don't. Simple as that. So what are they? Here they are, the big 3. Number 1, you have to say that electrons are transferred. That's the key action word. Number 2, you've got to explain that this transfer creates charged particles called ions. And number 3, you have to describe the attraction between these oppositely charged ions. Seriously, get these 3 points in your answer, and you are already most of the way there. So we know what happens, but why? Let's zoom in on our main characters here, the atoms themselves, and figure out what their motivation is. I mean, why do they even bother doing all this in the first place? It comes down to one simple word: stability. Just think of it like trying to complete a collection. An atom just doesn't feel right, it's not happy or stable, until its outermost shell of electrons is completely full. That is the end goal. That's what drives everything we're about to see. And this is where our story gets 2 very different characters. On one side, we have the metals. I call them the givers. They've only got 1, 2, maybe 3 electrons in their outer shell. It's just way, way easier for them to give those away to get to a full shell underneath. And on the other side, we have the nonmetals, the takers. They are so close, they're just missing 1 or 2 electrons to complete their shell. So for them, it's a no-brainer to just grab an electron from somewhere else. And this perfect setup between a giver and a taker brings us to the main event. This is the moment where the action happens, the moment that changes absolutely everything. So here's the play-by-play. First, the metal atom, our giver, gets rid of its outer electrons. By losing those negative little particles, its overall charge becomes positive. Meanwhile, the non-metal atom, our taker, swoops in and accepts those electrons. And by gaining those extra negative charges, its overall charge becomes negative. It's a perfect win-win transaction. And this whole process creates our star player, the ion. All an ion is an atom that now has an electrical charge because it either lost or gained electrons. You have got to remember this word. It is absolutely crucial. Okay, so now we have a positive ion and a negative ion hanging out. The big electron transfer is done. So what happens next? How does this actually become a bond? Well, what happens is that these 2 oppositely charged ions are now powerfully drawn to each other. And this force has a special sciencey name that you absolutely need to use in your exams. It's called electrostatic attraction. And that leads us to this, the perfect textbook definition sentence. Seriously, if you write this down in an exam, you are hitting the bullseye. An ionic bond is the electrostatic attraction between oppositely charged ions. That's it. And hey, don't let the fancy term intimidate you. At its core, it's the exact same idea you've probably known for years. Opposites attract. A positive and a negative will always pull toward each other. That's all electrostatic attraction really is. Now, imagine this whole process doesn't just happen between 2 atoms. Imagine it happening between millions, billions, trillions of them. What you end up with is this incredible, super organized, repeating 3D structure. It's like a perfect grid of positive and negative ions all locked tightly in place. And we call this a giant ionic lattice. So now, let's see how this story about tiny atoms explains something you can see every day. Like, why is it so ridiculously hard to melt something as simple as table salt? No, really, think about that. Your oven at home, cranked all the way up, might hit 250 degrees Celsius. To melt salt, you need to get it to over 800 degrees. Why? Well, the answer is hidden inside that giant ionic lattice we just talked about. Okay, part one of the answer is this. Those individual forces, that electrostatic attraction between each ion, are incredibly strong. Just think of them as millions of tiny, super powerful magnets all gripping onto each other for dear life. And here's the kicker. To melt something, you're not just trying to break one of these bonds. You have to break millions and millions and millions of them, all at once, to get those ions to break free and flow like a liquid. And overcoming that many strong forces takes a massive amount of energy. And we supply that energy as heat. That's why the melting point is sky high. All right, let's wrap this all up with a quick fire checklist to lock this information in. This is your final guide to writing that perfect answer and, more importantly, avoiding the classic mistakes. You gotta use the right language, okay? Say transfer of electrons, never, ever sharing. Talk about the electrostatic attraction between ions, not just that atoms attract, and describe the whole thing as a giant ionic lattice. These are the keywords the examiners are just waiting to tick off. I really can't stress this enough. The single biggest, most common mistake you can make is saying that electrons are shared. That word describes a totally different kind of bond, a covalent bond, and if you use it to describe ionic bonding, you'll get 0 marks for that question. I'm not kidding. It's an instant fail for that part. So look, if you walk away and forget everything else, just burn this little mantra into your brain. Metal loses, nonmetal gains, opposites attract. That's it. That is the entire story of the ionic bond in a nutshell. And I'll leave you with a little brain teaser to think about. We've just established that salt is made of a giant lattice packed full of charged particles, right? And we know that electricity is just the flow of charge. So, why can't a solid crystal of salt conduct electricity? The answer is directly tied to everything we just talked about. Give it some thought. Thanks for watching.